Okay, welcome. So this is going to be a lesson from our new unit called Probability Distributions. And we're continuing from Unit 3 on Probabilities. And today's lesson is actually also called Probability Distributions. So let's get going. So if you remember back in Unit 3, when we found probabilities, the emphasis is always on individual outcomes. So roll a die and you get a 4. What's the probability of getting a 4? And here in Unit 6, we're going to consider the full range of outcomes. So we developed this model, and we want to be able to show all the possible outcomes. So that's what a probability distribution is. It shows all the probability distributions for all the possibilities in an experiment. So if you take a die and you roll it, there are several possibilities. You could roll a 1, 2, 3, 4, 5, or 6. Okay, so each of those probabilities is actually equal, and we can show that in a table. It's really simple. There's 6 outcomes. Each outcome is denoted by x, and they're all equal probability, 1/6. So we can show that in a table form and also display that graphically. So in our graph, for our y, we have probability, and for our x, we have, in this case, the outcomes, the number rolled, okay, with an appropriate title. And it looks just like a bar graph, which we discussed last unit. Another thing to note, anytime you look at a probability distribution, all the events, so here there are 6 of them, the probability of all these events within the experiment always needs to add to 1. Add all these 1/6 up and you're going to get 1. When all the probabilities are the same, 1/6, 1/6, 1/6, there's a name for that. And we call that a uniform distribution. Okay, example 2. We're going to roll a pair of die. And if we can think back, we had a dice chart. And it shows you the different events rolling a 2 all the way to 12 and what their probabilities are. So we're going to use this information here into a table. And we're going to list those different rolling events. So rolling a 2 all the way to 12. And you can go through and using the pyramid or just thinking about it, how many ways can you roll a 3? Well, you can roll a 1 and a 2, or a 2 and a 1. So that's 2 ways out of the 36 possible ways. And that's 0.0556 probability. So think of a 4 now. You want to roll 4, you can roll a 1 and a 3, a 3 and a 1, or a 2 and a 2. So you continue doing this, and you eventually build a table that has all the probabilities, and they have to sum to 1. Okay? So every one of these probabilities represent the distribution of probabilities of rolling a pair of die. Again, you can show that graphically. So along y, we'll have our probabilities, okay, and you can choose an appropriate scale. So the highest percentage we have goes no higher than about 0.2 or so. So we went up by 0.02 per square, as you'll see here. And along the bottom, you have your different outcomes, 0, 1, 2, all the way to 12, because that's the way you can take 2 die. They can't sum any higher than 12. And once you graph that, it's discrete, so they don't continue. You use individual little, almost like lines with dots on the end of them. And you get this nice distribution. And it looks just like our pyramid. We actually say that this is symmetric. Okay, and because it's only one possible way of getting a 2, you can't get a 2.5, 2 and a bit, and you can't get 3 and a bit, 4 and a bit, so they're discrete. It's exactly 2, exactly 3, exactly 4, 5, 6, all the way to 12. So we say that this is discrete. Example 3 now. We've got these computer hard drives. And they're in an internet cafe, and they give you the following. There's 7 of them, have a 160 gig hard drive. So that's a gigabyte, GB, means the size of the memory, and it's abbreviated with GB. So there's 10 computers with 200 gig. You can see the rest. First thing I want to know is how many computers total. I add them up and I see there's 25. Okay, so we're going to work with tables. Okay, yeah, it's important to note that it's randomly assigned when people come into the cafe. We're going to work with these tables to do these probability distributions. So let's list all the different hard drives and figure out the probability that you randomly get the 160 gig hard drive. Well, there's 7 of those. There's 7 of those out of a possible 25. So the probability you get that particular hard drive, the 160, is 7/25, 0.28. And then there's 10 ways to get the 200 gig hard drive. So that's 10 out of 25. And you just continue doing this for all the types, and you build the probability distributions. Again, if you were to add this up, it has to add to 1. Use that as a check, because if it doesn't add to 1, you've made a mistake. Okay, now we're able to graph this, and again along Y we have the probabilities, and our highest one's 0.4, so we went up to put 0.5, 0.1 every 2 squares here. And along X you're going to have the hard drive sizes. Again, you get this discrete looking graph. Okay, it is not uniform, and it is not symmetric. Nonetheless, it's still a valid probability distribution. Okay, let's move into something a little different, but it ties into the probability distributions. It's this concept of expected value. This is really important. We're going to calculate this and use this quite a bit. So let's discover what it's about. The expected value of an experiment is the result that would be expected with one random trial. So if you go back to example 3 with the hard drives in the internet cafe, and there's 25 of them, different size of memory in gigabytes. What would you expect the size hard drive you'd receive if you'd come into this cafe? Which one do you think you'd get? What's the most expected one? Sort of a way to calculate this. Okay. Well, there's this big formula we use. Okay, it's not big. It just looks big because you see this sigma symbol, and you recall to yourself that that means to sum. Well, what do we sum? We sum all the different possibilities times their probability. Let's use an example so we can understand this a bit better. Okay, so this is the long way of writing this. The sigma symbol means you take all the different x, multiply them by the probabilities. Well, back in the internet example, there were 4 possibilities. So let's go back to that. And the expectation is the sum of the 160 gig hard drive. Where did the 0.28 come from? Let's go back. The 160 gig hard drive had a 0.28% chance, a 0.28 or 28% chance of being selected. So what you do is you take the 160 gig hard drive, it's the X value, times its probability. And do the same thing for the 200 gig hard drive. It was 0.4 for probability, and then the 300 gig hard drive was 0.16 probability occurring, and then the 80 gig hard drive was 0.16 probability occurring. So each outcome is multiplied by its probability. Sum those up, and that's the expectation. It's kind of interesting. When you sum these up, the expectation becomes 185.6 gigabytes. So of all the possibilities you could have gotten, the 160 gig, the 200 gig, the 300 gig, and the 80 gig, it does weigh out that you're going to get an expectation of 185.6 gig. That's not possible, but that's still what the math tells us. Okay, it's almost like a weighted average. Okay, let's take another look at some more expected values. So go back to examples 1 and 2. Example 1 is about rolling a single die. So we have a die, and get the numbers 1, 2, 3, 4, 5, or 6. Uniform distribution, they're all probability 1/6. So if you take that, it's the outcome 1 times 1/6 it happening, which is probability, outcome 2 times 1/6, etc. And you're going to find the expectation of rolling a die is 3.5. And you're going to say to yourself, how do you roll 3.5? You can't. But the expectation is still that you would normally roll, if it even were possible, 3.5. Example 2, if you roll 2 die, this is a little longer. There's a lot of outcomes. There's the outcome 2, 3, 4, 5, all the way to 12, and individual probabilities for each. So the expectation is quite long. You've got the expectation is rolling 2 is 1/36, plus rolling 3 is 2/36, etc., all the way to rolling 11, which is 2/36, plus 12, which is 1/36, and you add that all up, and the expectation you're going to get for rolling 2 die is 7. And I know we just had the carnival, so I wanted to discuss something interesting. In the game Craps, 7's really important. In fact, when you roll a 7, it's called Craps, and it's 100% based on probability theory and expectations. The game is devised solely on this type of math, and it's just interesting that there's this connection. Okay, so example 4 is one for you to try, and it asks, what's the expected amount won on each ticket? And then a bit of an enrichment. How much should the grad committee sell the tickets for in order to make a decent profit? So pause here for a sec and give this a try. We can talk about it in class. Okay, last thing's a bit of definitions, a bit of some properties and other things to mention regarding probability distributions. So when we deal with a probability distribution, we talk about a random variable, capital or uppercase X, and then that random variable can have various outcomes, which we denote X. So all throughout this lesson, we've mostly been talking about little x, and there are different kinds of little x. You roll a die, you can get numbers 1, 2, 3, 4, 5, 6. Well, rolling that die, and the numbers 1, 2, 3, 4, 5, 6 have to fit random variable, and the outcome's X. So let's show you how that's done. So you got a single die. The outcome of rolling the single die, that's the random variable X, okay, capital X. And each event, 1, 2, 3, 4, 5, 6, would be represented by lowercase x. Go back to example 2 with 2 dice. What's the random variable here? Okay, and what's lowercase x, the outcomes? Well, the outcome of rolling 2 die would be the random variable. That's the random thing that's happening. You roll 2 die. Okay, x represents the different sums that could be rolled. So x could be sum of 2, 3, 4, all the way to 12. In example 3 with the hard drives. Okay, so the random variable here and x were the following. So the random variable was the size of the hard drive. Okay, what size hard drive were I gonna get when I'm coming into the internet cafe? Well, the possibilities are little x, the different sizes, the 80 gig, 160 gig, okay, etc. There were 4 of them. All right, so x can only be some fixed number. It can't be continuous, okay? We consider that to be discrete. So going from 1 thing to 2 things to 3 things to 4 things, not 4.5, not 4.777, but exact numbers, think of it like that. Those are discrete probability distributions. And the other kind you can have is a continuous probability distribution. And we say there's infinite possibilities here. So a quick example to highlight that. Example 5. If you consider the height of males between the ages of 18 to 65, we've listed some heights and their probabilities. And you see here that there's no fixed number for the random variable x. We could have various heights, and I mean, this is a limited list, but you could have various amounts. It can keep going. You could have gone to 5'9", 5'10", and there'd be different probabilities. So in a sense, it's somewhat infinite. And again, you can still graph this, and it's the same kind of graph. We use probability for y, okay, and then along here is the random variable capital X height, and all the little x's, 5 feet, 5 feet 1, etc., all the way to 5 feet 8. And it takes on the form of almost like a bar graph, Okay, but it's not quite a bar graph, it's more of a distribution graph. Okay, so there's lots of content in this video. I recommend you go back and perhaps review any of the new terminology, any of the new calculations, any of the new formulas, graphs, and to reinforce what you've learned, you should try these practice questions and bring them to class so we can work on them. So in your workbook, page 103, number 2, 5, 8, and 9, bring your questions, and we'll see you in class.